Hi, welcome back to Moose in Chemistry. This is electron configuration of the element europium, EU lesson. Okay, europium happens to be element number 63, so we're going to write 63 for our atomic number. And its atomic mass number is 152. So what we're going to do is we know that since the atomic number is 63 and that represents the number of protons, we have 63 protons. We also have 63 electrons since it's electrically neutral. And to find the number of neutrons, all we do is subtract the AMU minus the proton count. So we go AMU minus protons equals neutrons. Pretty simple. So you go 152 minus 63, and you get 89. We have 89 neutrons. Pretty darn snarly, I would say. So go ahead and take care of that. Okay, so now, remember that S suborbits can only hold 2 electrons, P suborbits can hold a total of 6 electrons, D suborbits can hold 10 electrons, and the F suborbits can hold 14 electrons. We're going to use something called the off-ball principle, which says you have to fill the lower shells first before you fill the upper shells. Okay, we're going to use this thing called the diagonal rule, which is right here. So we're going to start with an X right here at the top and pretend that we're sliding down these slides until we run out of electrons. Okay, so we go 1s2, and then come down 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, and 4f7. You add all that up, that equals 63. Pretty darn snarly. Alright, now we're going to do orbital notation. That's Hund's rule, where it clearly states that we put an up arrow in every suborbit, and then we can do the down arrow of that suborbit. Alright, 1s is pretty easy. It's just up and down. 2s, up and down. And watch this. 2px, 2py, 2pz. There are 3 ups. According to Hund's rule, now we can do the downs. And see how that works? Pretty darn snarly. Up and down. We'll do it again with the 3px, 3py, and 3pz. Watch this. Up, up, up. Stick one up arrow up in every suborbit. Now you can start the down arrows for that suborbit. And that's Hund's rule. Up and down. And we just keep on going until we run out of electrons. Pretty amazing. Okay, we're almost there. Okay, so now 4px, 4py, 4pz. We go down, 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 then up, and then down. And then we're going to do our 4d10s. So 1, 2, 3, 4, and 5. Then 6, 7, 8, 9, and 10. Now 5p6, 1, 2, 3, 4, 5, 6. 6s up and down. Now we have 7 left. So we go 1, 2, 3, 4, 5, 6, 7. Okay, and that's it for the Hund's rule. Now, what we're going to do is we're going to do our noble gas notation. Now, to do that, we have to see what period it's in, because we've got to pick the nearest noble gas. It looks like it's in period 6, but it's not. Remember that F block is n minus 2. So you would go 6 minus 2, which means it's in the 4th period, right? So since that's in the 4th period, we have to figure out the nearest noble gas. Well, the nearest noble gas would be xenon, okay? Xe. And then we would write it. Now, xenon is going to take up all of this right here. That's xenon's electron configuration, actually. So in essence, noble gas is like shorthand. It takes care of a lot of the missing, not missing electrons, but you know, all the ones that are like not the outer electrons that are working. And so you go the core electrons, is what I'm trying to say. 4f7, 6s2. All right, now what we're going to do is we're going to do the quantum notation next. The quantum notation is where we have 4 unique numbers that represent that element itself. Okay. So here we go. So let's see here. It's in the 4th energy level. So we put a 4 there for our n. Our angular momentum number, our L number, is 3 because it is in the F block. Okay. And then it's the 7th one over, so it's -3, -2, -1, 0, 1, 2, 3. So it'd be 3 positive. And the last arrow, of course, is going up, right? So it's going to be 1/2 positive. Well, that's it for this element. You guys be snarly, and we'll see you back here at Musin Chemistry.